Okay, last lecture of the semester. So today we'll try to do a run through of everything that we've talked about in class. Of course, it's going to be kind of a high level, and I would very much welcome questions along the way. If there's anything that you feel you didn't really get, we'll spend 15 minutes on that and skip some other parts. About the exam, it's open book. Sorry, it's closed book except for the source code, which is open, and you can have any handwritten notes you want in there. It'll be here between 1 and 3 p.m. Neil and Jana will be proctoring. I'll be available online. I'll be in New Zealand, actually. That'll be awesome. But it's only a 5-hour time difference, so I think it'll work out.
It's not cold enough here for you?
They're in summer there now, so it should be pretty nice.
Oh, yeah.
I expect to go swim.
I was thinking somewhere else. Yeah, that's going to be really nice.
Yeah. Okay, so anyway, the point of the operating system, I suppose, is to take this machine that can do almost nothing on its own and make it this nice and cozy environment for processes and users. So let's start with what the machine provides. So at the very fundamental level, we have some hardware instructions executed in order. I'll put that in quotes. It'll always appear like they execute in order, but they don't actually. And you'll find out if you try to measure performance, you can notice that they don't actually run in order, but there you have it. Okay, so these hardware instructions are mostly just your run-of-the-mill ALU instructions like adding, multiplying, and such. And then we have direct access to memory. And by that I mean RAM. So that's pretty much it. Then we have an interrupt control, some interrupts provided. When triggered by hardware events. And that would be external hardware like a disk drive or a timer. The timer is considered external, although it's usually on the same chip. And then there's, I guess, one more thing, and that is we have some ports that we can use to talk to sort of peripheral hardware. So we have our in and out read-write instructions for ports to peripherals. So the most important peripheral here would be a disk drive. So there's a standard sort of convention in the, in the IBM AT standard or something like that. Since then it's been the case, you can write to port 2F8 or something and put a certain value in there, and you'll get the behavior that you expect from the first disk. So that's sort of how we get started with everything. And you can find the details on that in the IDERW.c. There it's doing all this. That's the driver for our in the OS. Okay, but so this does not have any support for, all right. So a couple little things more that we'll add as we go. But there's no support for processes. Right? System calls don't exist. There's certainly no higher level language and that sort of thing. And so we want to, there's no ports, there's no shell, there's no anything. We can just run our hardware instructions. So we have to provide these instructions, but how do you get started? And that's the boot. I'll add a couple more things that the machine provides. We do have virtual memory hardware. We call it paging hardware. And then we have dual mode execution with some privileged instructions. So here, dual mode execution, by that I mean this user supervisor mode. When you're in user mode, you pretty much can only do access to memory and the normal instructions. You can't do anything with the virtual memory hardware. You can't run your in-out. You can't talk to peripherals. Pretty much you can just read and write to memory. And that's it, except for there's this one instruction, or two instructions, syscall or int, which actually go from user mode to supervisor mode. And then that's sort of what we use to create the process abstraction. Okay, but to get started, if we want to run anything at all, we have to get the machine to run some instructions. Those instructions have to end up in memory. How do we do that? Well, when the machine first starts up, there's some built-in software called BIOS. So there's some convenience routines in there. We recognize you can change the video mode, you can put some characters on the screen, you can read from a disk if you need to, although you could just use the in-out port stuff there. When we first boot up, we start in 16-bit real mode, an ancient mode of the x86 family. It's mostly provided for backward compatibility. It's really convenient in the sense that you can still run your 16-bit code on a new machine. Okay, so when we first start up, after BIOS is done initializing, and by initializing hardware, it could be things like maybe setting all the memory to 0, or it could be, say, spinning up the hard disks, or it could be setting a video mode so that you can see something on the screen, that sort of thing. BIOS loads a boot sector, from the first disk that has one. All right. So BIOS will look through the disks it can discover, and it has a bunch of drivers built in. This is a relatively big piece of software. It usually comes with your motherboard. Sometimes you can replace it by another BIOS, but generally you don't. It has all sorts of drivers for various kinds of disks and such. So it'll look through all the flash drives and the floppy drives and the CD-ROMs and the hard drives and all that. It's got all the drivers for that. It'll see, okay, which one of these actually has a boot sector? It'll go in some order that's defined in BIOS menus, and then it'll load that boot sector into a certain address in RAM. Does anyone remember? No. 7C00, yeah. That's not going to be on the exam. So it loads it to this specific address in memory and then just jumps to that address. And after that, BIOS gets out of the way. Let's see. To 7C00 and jumps to it. So after this, it's sort of up to us. We have all the instructions. We're running in, there's no super user mode in 16-bit mode, so we have everything at our disposal. Yeah.
Is there a particular reason for 7C00 or was it just arbitrary?
Well, maybe there was a reason way back when. Now there certainly isn't. But if you have an old boot sector that's linked for 7C00, it's not going to run if you load it to somewhere else. So, well, it can. But if it has any static addresses in there, yeah. So generally it's best to not fix what isn't broken, I guess. Okay, so where was I? Yeah, so we're now in 16-bit mode. Now it's up to us to decide what to do next. It can be a good idea to rely on the BIOS routines to kind of get a little bit more done. So now if you want to load some more data from a disk, say you want to load the kernel from a disk, it might be better to use BIOS to do it. BIOS supports all sorts of other devices than just the standard hard drive. You could even boot from a network with a BIOS, and it would work the same if you just say, read from disk, and BIOS will pretend that the network is a disk, and that's fine. So anyway, we have some BIOS subroutines already available in memory. We can call them by this int thing, put some arguments in various registers, and BIOS will do what we want, but we don't need it. If we have the code, if we already know which instructions we need in order to do the work that we need to get done, we can just run those instead. BIOS has no special instructions. It's all no special privileges or anything. It's all the same instructions as everyone else. It's just that it's a relatively large library. It's already in memory. Maybe you want to use it. We have the problem that we get 512 bytes. One sector. And we don't even get to use all of them. We really didn't talk about that, but there's partitioning information and stuff hiding in there. So there's less than 512 bytes we can use. At the very end, there was this AA55 that says that this is a boot sector. Of course, there's no guarantee, but chances are it's a boot sector if there's an AA55 at the end of those 512 bytes. Right. So one thing that that you often end up doing is, you put some more code in the next few kilobytes or megabytes, and you just load those sectors straight into RAM and jump to that, so that you now have a little bit more to work with, because we're kind of spoiled and used to working with megabytes and not individual bytes of memory. And then we can load, we can sort of mount a file system if you want from this boot sector. Boot sector becomes a little OS of its own. Grub, if you've heard of it, it's like a whole little operating system on its own. It's got a command line, it's got all sorts of file systems, it's got all sorts of commands. And so that's one of those secondary bootloaders. And it'll mount the file system where the kernel is hiding. It'll find the kernel file based on the path that the user provides, and then load that into memory and basically jump to it. And then it's up to the kernel after that. Okay, so once we've started running the kernel, now it's up to the kernel to kind of set things up. We see it in main.c. We see most of the setup. There's a little bit of this in entry as well. Before you can start running C code, you have to be in a sort of sane environment that C expects. So we have to be in the right mode. We have to have pages mapped in. We have to have probably a way to allocate, actually. No, we don't need a way to allocate memory, but we need at least a stack set up in a sensible place. There's a few things like that. It's a good idea to take a second look maybe at entry.s to really see what's going on there. And boot asm will also do a few of these setup things, mode switches and stuff, and then there's some more of that in entry.s. It's only a good idea to look at this to kind of get a feel for how primitive the machine is to start out, like what little there is to work with. But then once we get into C, that's in main.c, now it's pretty simple. We're just initializing a whole bunch of data structures. I think the most important of all those data structures is probably the free list that we initialized in the very beginning. For all the pages of memory in the entire machine, we just add them all to a free list so that we now have a memory allocator available to us, kalloc. That's really convenient. Another thing that we set up very quickly is the interrupt vector. Let's see. OS boot. Memory allocator. There's the interrupt vector and system call setup. So basically we're saying, okay, if an interrupt comes in, what are you supposed to do? In the interrupt vector, we specify addresses of functions that should be run when a certain interrupt happens. The same is true for system calls. In x86, there's like a little stub routine. It's just like 2 instructions. For every interrupt, there's a couple of instructions, and basically they jump straight to trap asm. What is it called? All traps in trapasm.s. So all the interrupts get processed there, and then we have, for the system calls, there's something similar at the I don't remember. Systrap entry, is that it? Oh yeah, that's it.
The entry for
Yeah, so there's There's a little bit of stack manipulation happening in entry, but all of the actual system call handling then goes inside of all traps as well toward the bottom there. They're very, very similar, interrupt handling and system call handling. But basically we're saying, oh, if an interrupt instruction is run, or a system call instruction is run, or any sort of hardware interrupt happens, go here. And that's the fundamental basis of the operating system, that we can take over control when these things happen. So generally the OS doesn't actually run, right? When you're running a process, you're not running anything else. At least a single core CPU like this will only be running one thing at a time. It'll mostly be the process, and sometimes you'll be running kernel instructions, almost always on behalf of a process. Yeah.
You mentioned how when a system call happens, it's just putting an entry on the RX and calling the syscall instruction, and the syscall, and then we move to syscall entry where the processing actually happens, right? Where is the mode switch actually happening from user to privilege at the CPU level?
Yeah, so the mode switch happens immediately when you run the int or syscall instruction. It'll put a couple of things on the stack and basically atomically put things on the stack and then switch to the supervisor mode and jump to the right place. So there's no space in between where the user can kind of intervene and say, well, okay, now I'm supervisor mode, let me run these instructions instead. It basically happens in one big chunk.
So the syscall instruction itself does that. We don't have to do anything.
Right, exactly, yeah. That's the whole point of the syscall instruction and the int instruction. So one can actually easily implement system calls with the int instruction as well. There's no real difference there. Syscall is just a little bit faster because there isn't as much that you really need to handle when you're managing a software system call as opposed to a hardware interrupt. Yeah.
How did it know what the address was of the first instruction to go to in the trap frame? When it when you interrupt or call the systrap or the system call, like how did it know where to go after that?
Okay. So for syscall, it's a little bit special. There is it's called an MSR, manufacturer specific model specific register called L star, where you put this address. You'll find it probably in VM.c, EMINIT, something like that. For the interrupt, it's the interrupt vector table, or is it the interrupt descriptor table? Vector? I don't know. It's called from main. It says L. Actually, we should take a look at this, make sure we get it right. Yeah. Okay, so let's see here. I think it's called TV init. Yeah. So here in main we call TV init. There's a bug in this version of the source code that you have printed. There's two calls to TV init. It doesn't cause any trouble, but it's a little unnecessary. And so here it is. So we're saying for every. Okay, so do we have the make gate defined? We don't. But basically, it just initializes this array. Sorry? That's make gate? Oh, it is. Oh, nice. I thought it was a macro for whatever reason. Right. So this is just initializing this array. The interrupt descriptor table has all these addresses in it, and it also says some things about where it can be invoked and sort of thing. What's really important is, for this interrupt, for interrupt number 5, which is the address we should be calling? I would say that's the address. This is the interrupt number. That's just the base address of the table. And then this is whether it's like a software cost. Okay, I'm not exactly sure actually what the difference. I forget what the difference is between a trap gate and an interrupt gate. We'll ignore it. Oh yeah, so it's I think that one of them can happen from user space and the other one can't, or the other way around. Either way, basically it's just a lookup table. So for this number, that's the address we want to jump to. And then while we're at it, maybe we should go look for our L star thing here. So here we're saying for system calls, it actually does it another way. So we still have it. We kind of skipped it now, but there's also the code for, in the interrupt table, there was also code for the system call interrupt. It used to be an implementation of system calls that used interrupts, but I decided to switch it to the conventional syscall instruction for the 64-bit version. Okay, is that pretty clear then? Yeah.
What's WRMSF?
Okay, so this is write model specific register. It'll just be an instruction like that, I think. Actually, let's see, but I think the instruction is called exactly that. Yeah. So I guess WRMSR takes some parameters in some registers and then writes it into that model specific register. There are many of those. They do all sorts of arcane things that aren't fundamentally important. In this case, it's not fundamentally important either. When you have to put it somewhere. Where is the system call entry point? That's where you put it. In other cases, we have this CR3, right, for the page table. That could just as well have been another model-specific register, except it's not model-specific. It's across all of the x86 protected mode CPUs. So I guess they keep that in its own register name. There are a lot of these kind of arbitrary choices in the hardware, and we just live with it. Okay. Backing up. After this, there's all sorts of other initialization of various data structures and caches and such that we can kind of ignore. Toward the end, we create the first process. That's kind of important. So the first process is very special because processes are created by forking. But there isn't a process yet, so you can't fork. Right? Fork is a system call, and generally system calls are very hard to call from inside the kernel. Usually they have this expectation. They're implemented with this expectation that proc has a value, right? Just from a very concrete standpoint. And overall, the context is you're supposed to be calling system calls from within a process. So we don't have a process, so we kind of have to fake it. And this is the init proc, I think. Is it init proc.s? No, it's not. What's it called then? Well, it's not so important. Actually, let me see where it is. Init code.s. So init code is a very stupid little program. It just makes one system call to start to replace itself with init instead. Init is a proper program. Init code is a tiny little bit of assembly that doesn't actually sit in a file. It's part of the kernel, and because we don't have a process yet, we can't really read files, because you read files with system calls. And so we keep this little bit of code somewhere in the kernel, and we just copy that to address 0 in a setup kind of virtual address space, and then we jump to it, or we return to it after setting up all sorts of fake values in the trap frame for this newly initialized, so far dead process. We then return into the process as if we came from there, and then we very quickly just execute one system call, which replaces that silly process with init, which is now our first proper process. Init is the first real process. So on any Unix machine, it'll have process ID 1, I think. So from there, init doesn't actually do much. In our case, I think on a Linux machine, init probably starts up the process that runs through all the initialization scripts in /etc/rc. There's a whole setup process to load drivers and to mount file systems and to do whatever they start all sorts of programs, and that all comes from init because init is the first process. The only way to start the rest of them is by forking init and then execing something else. Our init just runs sh over and over and over and waits for sh to finish and then runs it again. Sh doesn't usually finish. Okay, so then we're up and running. So init starts sh. Now we have sh and init running. We usually, that's the kind of a common state in an x86 virtual machine. We have two processes, and then maybe we run one more. But we can support any number of processes. Well, not any number, up to max proc processes at this point. So now the question becomes, like, how do we make the machine run multiple processes at the same time when it can only run actually one process at the same time? It'll only follow one sequence of instructions, and we'll want it to run both at the same time. Actually, we don't really care if it runs them both at the same time. It should just look like it. Right? And that's the basis for a multitasking OS. For the typical user, it doesn't matter if we don't switch all that often. If we switch 1,000 times a second, that's plenty. And that's what we do. So let's do scheduling processes. Okay, so a process, start with that, has its own virtual memory layout. Its code runs only in user mode. Oops. So its own virtual memory layout, that means it has its own page table. Right? These page tables in 64-bit mode are pretty huge. There's 4 levels, I think. There's a PML4, the PDPT, the PDE, and then a page table. And then, of course, the pages below that. So there's a big hierarchy. Generally, the hierarchy isn't all that full. At least when we run in x86, it ends up being, the first level is just 2 entries filled in, one for the kernel memory and one for the user layout. And then next level, there's just 1 each. And the next level, there's maybe also 1 each. And then there's the page table in the end that's kind of full. So it's a big, tall hierarchy, but it's not very sparsely, very densely populated at least. Okay, so right, meaning its own page table. Runs only user mode. So if we want something done in user mode, all we can do is run the normal instructions and access our own memory, the memory that belongs to this process that's currently mapped in, and with a U bit as opposed to an S bit on those pages. Right? If the S bit is set, only supervisor mode instructions can access that memory. So if the process wants anything done, it'll have to, anything more exotic done, it'll have to ask the operating system for help. So to do, let's see, to access anything except mapped in memory registers system calls. So a system call is basically a question of putting a few values in registers and then running the instruction syscall. I don't think syscall takes any parameters. They're all sitting in registers. There's nothing sort of on the instruction itself. And then the CPU will stop running in user mode, jump immediately to whatever address was set in this L star register, and take it from there. So the operating system looks at the contents of the registers to decide what it's supposed to do next. In the beginning, it'll say, which system call did you want to run? Maybe that's in RAX. And the next one might say, like, what's the first parameter to this system call? Actually, I'm not sure now that the system call number goes in RAX. Let's take a look. Yeah, it's RAX. What's that? Yeah. So the reason I was thinking about this was the parameters come in registers that sort of look like the parameters for function calls. The first parameter will go in RSI, I think, and then RDI, and then so on. So RAX ought to be in that list. But RAX is used for the system call number, so I wasn't really sure what's going on there. Anyway, so those parameters, with RAX, we see which system call to run, right here. And then, I'm sorry, there, of course. This is the return value on that line. And then we get the parameters, and why don't we take a look at that too? Arg int, I think it's called. Okay, ought to be very close to here somewhere. Here, okay. Right, so here it is. We have all these system call implementations like sysread, let's say, that takes a bunch of parameters. They all use these arg int, arg adder, and so on functions to kind of pull out each individual argument. And in a 32-bit implementation, you have to do some stack arithmetic. In 32 bits, the parameters come on the stack. In 64 bits, the parameters come in registers. So here is the bit of code that decides which register holds the first argument to the system call. So it goes RDI, RSI, RDX, R10, R8, R9. And apparently we can only support 6 parameters to a system call. Okay, so the point of the system calls here is to provide privileged kind of operations to the application, but in a safe way. So you could imagine if an application could directly talk to the disk, they could easily make some mistakes. They could end up, say, overriding some sectors that didn't belong to the application, and we'd have all sorts of trouble. But when we're running it as a system call, the OS can first make some checks and see, are they allowed to write to this block, right? Or in the case of a file system, the OS is a little higher level than that. You can't even issue a system call saying write to this block. It'll say, I want to write to this file, and the OS makes the whole translation, of course, between the file and the individual disk block. But in either case, the OS is there to provide safe sharing of these resources. Resources that are shared would include the disk and memory and the CPU, and of course all sorts of other stuff. But so memory we're sharing by means of the page table, or the paging mechanism. And so the kernel code gets to say which pages belong to this process, at which point the process can have free access to those pages. The kernel doesn't get to see when the process accesses memory. Actually, that's only almost true. There's a little bit of evidence that a process has accessed memory. Anyone remember? So we don't get to directly see that, oh, look, the process is accessing memory, because the kernel isn't running, so there's no way to observe this.
I think it's a bit set on the page itself.
Exactly. So in the page table
Access
entry,
bit.
there is an A bit. This is accessed. So if the process has accessed this entire page at all, and the kernel decides to go and take a look at this page table entry, it'll notice that the bit was set to 1. And it can set it back to 0, and then at some point later it is a 1 again, so now it can kind of tell that there's some accessing going on. That's actually used for the purpose of LRU cache management in the kernel, not in x86. Right. There's also one for the page has been modified, the dirty bit. Right, so that was the sharing of memory. So the kernel kind of owns all the pages, and then it assigns some pages to each process. And then there was the sharing of disk. The individual disk blocks are not really provided to applications like that, but the kernel at least controls, it owns all the disk blocks and says, these disk blocks belong to that file. These disk blocks belong to that file. And it can also then impose constraints on users. If you have enough code in there, you can have user quotas and all this stuff in your kernel. And what about the CPU? So the CPU is also a shared resource. That's probably the most scarce one, because usually there's just the one. And it needs to be shared mostly between applications and a little bit by the kernel. So by the kernel itself, right? Usually the kernel is executing system calls. System calls are basically, we're still running the process. It's just that we're running a very tightly controlled set of instructions that are sort of trusted to execute correctly. Whereas user program can be anything. When the user program makes a system call, it starts at a specific place, runs these very specific instructions that we know are safe, and then it returns to the crazy world of user space again. Where was I going with this? Oh yeah. So now we need to share the CPU. How do we share the CPU? Well, let's see. Sharing the CPU. This is called multiprocessing. There's a couple different ways. You could have each process say, well, I'm done with the CPU. So it doesn't work and it's done. Or maybe it does some I/O, and when you do some I/O work, well, then you give the CPU away because you're going to wait forever before the disk or the keyboard or whatever responds anyway. So you could have cooperative. Sometimes it's called multitasking. Cooperative multiprocessing, where processes yield the CPU explicitly. So here, the process being user level code issues the yield. Or maybe not. Well, user level code at least kind of does something to make the yield happen. So it might make a system call that wasn't meant to yield the CPU, or it only wanted to read from the console, but at least it wasn't just running a while true loop. It did something to make this happen. That's cooperative multiprocessing. And then there's preemptive, where a timer limits execution. So here, no matter what you're doing, you're running in user mode, any instruction, at some point a timer goes off and that's it. Now there's a timer interrupt, we switch to the kernel. In fact, we're still running the same process, right? When a timer interrupt goes off, we're still in the same process context in some sense, but the timer interrupt handling code generally would then say, oh, it looks like I've run enough, let me switch to another process. This is not cooperative, even though we're running kernel code here with a certain process active, and the kernel code is voluntarily yielding the CPU. Well, it's not that the application yielded it. It was just it was sort of the kernel doing this without the cooperation of the application. Okay, so how do we switch then between different processes? So this is somewhat similar to what happens when you make a system call. And maybe before we go there, we should do a mode switch. So in the interrupt handler, we have to save register contents, switch stack to a kernel stack, and this is sometimes done automatically. For interrupts, it's done automatically. For system call, for the syscall instruction, it's not. It's done in entry, syscall entry. So we save away all the register contents, switch to the kernel stack, and then execute the system call code as indicated, say. And then we restore register contents, switch back stack, restore register contents, and then return to user space. Actually, I think it should go the other way around. Yeah. The reason it should go the other way around is all those register contents are sitting on the kernel stack, not on the user stack. Okay, so that's a mode switch, which I am not exactly sure about the context switch terminology here. People talk about context switching. I don't think that a mode switch is strictly a context switch, but I could be wrong. When you're switching processes, it's certainly a context switch. So process switch. So at some point, the process says, well, I'm done. This is always going to be in kernel code. We're running in the kernel. Maybe there was a system call that says, well, I'm done. But we're still running the system call yield. And then inside of there, there's finally the call that says, now we will change from running one process to running the other process. And let's see, always in kernel code. And what does it do? Well, what's really important here, I think, is that it's switching kernel stacks. So whenever you yield your CPU, yield the CPU, you store away a pointer to the kernel stack in your struct proc, and then when you come back, that pointer, stack pointer, is returned into RSP so that you continue running in the kernel where you used to be. So it's done in switch.s, and basically replaces, let's see, mostly switches the kernel stack, RSP. There are a few other registers, I think, that need to be stored away on the stack. I don't recall. So you call this function switch. You get in there, and now we're switching the kernel stacks, and then we return, and we actually return out into the other process. And that's not something I'm going to repeat the whole way here, but if you don't feel familiar or comfortable with the process switch yet, go through it a couple more times. Try to get it. This is a key piece of what's going on in the OS. Okay, so we switch kernel stacks. We're still running in the kernel, but now we've also changed the proc current running process variable. And we, at some point, so switch doesn't do that. Switch just switches the kernel stack, but we have to change so that we know which process we're running at the moment, and we have to change our CR3 to point to the new running process. Processes page table. Right. So if we do those three things, we switch to the new process's kernel stack, we set the proc variable so that we remember which process we're running, and we change the CR3. Now we're pretty much running the new process, but we're still in the kernel. Yeah.
You mentioned that we need to change the CR3 to some new process page table there. I mean, it makes sense. When the process is accessing any memory location, it goes to the page table. But does that not apply to the kernel? I mean, when the kernel is accessing a piece of memory, it does not go to the page table, or?
The kernel is a little special because it gets to have a mapping in every process.
Yeah, I mean, it's from turn-based and up, it's the entire mapping, so you can access it. But when we're accessing it, it's directly we can access the direct pages themselves, or we can access the.
Okay, so it's possible to turn off paging, but you wouldn't do that generally. So if paging is enabled, then you will always go through the page table, and in that case, you rely on every page table having some kernel code at least mapped in. Not every OS will map in all of memory above kernel base. It's not necessary, but it's very practical.
My doubt came from the fact that we are switching CR3 in the kernel. I was wondering if that would it doesn't actually affect the execution of the kernel code itself, but how is it not affecting it?
Okay, yeah, so it is affecting it performance-wise, actually. It'll evict some LRU entries and such, but in terms of just correctness, it doesn't make a difference because the kernel accesses kernel data, right? And that's all above kernel base. And so when you switch to a new page table and that page table looks identical, what's the difference?
When kernel base and up, it's the same anyway.
Exactly, it's always the same. And I think we can see that in setup KVM, perhaps. Yeah. All right. So here in setup KVM, that's called for every process. I think. Let's see what it's called. So here we're. Okay, so on exec, that's good. So we're going to make clean out the page table, right, for this new process. So the first thing we do is run setup KVM. So now we've set up the kernel mapping, and after that we start loading in other parts of the program into memory. So the ELF binary has all these segments that say, oh yeah, these bytes from the file should go here in memory. Those bytes should go here. These bytes go there. These should be read-only, these should be read-write, these should be supervised, these should be user, and so on. So here's the loader. You know, you talk about linking and loading. Linking is where you put together your program so all the pointers make sense. Sometimes it's done at compile, like statically at compile time, sometimes when the program is running with dynamic linking. Loading is where you just take all the various pieces from a binary on disk and stick it in memory. So here we are actually making the process virtual memory layout, and we start out by just sticking in the kernel mapping. If we go back, it's actually a nice little trick that we're pulling here. So you see we allocate this PML4, that's the top level page. Oh, it's top level of the page directory, or page table. So that's one page, and then we just map in an existing kernel page directory pointer table. So we're using the same mapping. The kernel mapping shows up in all of the various page tables. It's not like we have to have a ton of these big kernel mappings. It's just this is one page. It was allocated the same way some other time. But this one has the entire kernel mapping, and we just get it in with this one entry in the PML4. And then later on, there will be more entries in the PML4, probably at the very bottom of the PML4 to get the addresses starting at 0. Right, so here it's at 256 because the entire memory is 512 entries. And so 256 is halfway up the memory, and kern base traditionally is halfway up. Right, so yeah. Interestingly here, there's only, in a 64-bit machine, there's only 48 bits worth of address at the moment. That's because 48 bits of address is a ridiculous amount, ridiculously large, that is. So it would be a waste of resources to support those extra 16 bits at the moment. 100 years from now, maybe it'll make sense, and in that case it'll be a relatively easy port because all of the code is still 64-bit. It's just that now we're using addresses that have, not all ones at the top, or well, it's not all ones or zeros, yeah, but they're not all the same at the top. Either way, so now we're using the top 16 bits. There's some changes in the OS, but not much. Like the page tables will be one more level deep, or two more levels deep, I think. But for the applications, it won't make a difference, I think. So that's nice. We can continue running binaries beyond 48 bits when that time comes. Right, okay, so we do those changes, and now we pretty much are running the process, but we are running kernel instructions on behalf of a new process. And then when we return from switch, we actually return back out to where we used to be when that process yielded the CPU. So you kind of go into switch, and then later on you come right back out after whoever else wanted to run is done running. Okay, so then finally we back out, and eventually we get to the syscall trap ret in alltraps.s, where we restore all the register values that were stored in that old process that we just switched to, in the trap frame of that old process, which is sitting on its kernel stack. So now suddenly we're running in user mode, and everything looks the way it used to be when that process was running last time. So it's sort of seamless for the processes, and the intent, at least, of the design is that the processes can't tell when they're being switched out. Right? There's not really any detectable effect except for time. It's always like that. With the performance or time, if you start measuring that, then you can tell that there's something going on under the covers that isn't as it appears. Okay. So then there's threads. Threads are almost exactly the same thing as a process, except they share some things. Some process-specific resources. So threads have their own stack, their own register contents, but that's about it. There might be some thread ID and that sort of thing, but they share all the file descriptors. They share the virtual memory. There's only one page table used by all the different threads. They share a parent process and such. So switching between threads is the same thing as switching between processes, except you don't have to worry about the CR3 really. For the rest, yeah, you have to do it all. Okay. I think we should move on to virtual memory. I guess we're pretty much set with the virtual memory. Well, you should read up on virtual memory if paging doesn't sound familiar, but I'm sure with all these homeworks you probably have a good grasp on it. So let's move on to, we discussed interrupts, but let's talk a little bit about concurrency. So interrupts are one source, let's see. One source of concurrency would be interrupts, meaning, by concurrency I suppose I mean that things happen to your memory mostly that isn't immediately obvious from the instructions that you're running. So you run a bunch of instructions and then other memory changes at the same time, or the memory you were reading changes in ways that you didn't say. So we can get that sort of behavior from interrupts, because an interrupt can just stop executing your stuff seamlessly and then make some changes and then go back to running your code, and some changes happen to memory sort of in between two instructions. You can also get concurrency when you have multiple threads, because multiple threads share one setup of virtual memory, so they would, if when you're switching between threads, well, I guess that's usually interrupt based, but let's do that anyway. So with threads, they're sharing memory, and they might be, one thread might be modifying the memory that another thread is looking at, sort of at the same time, and again you get this confusion where things aren't as they appear when you just look at the sequential code. And then finally there's parallel hardware, multi-core machines in particular, or SMP machines. So SMP means multiple chips on a motherboard. Multi-core means multiple cores inside of one chip. For all intents and purposes, the same thing. So here you're actually running two sets of instructions at the same time. Oh, there's also SMT, simultaneous multi-threading, where you're running two threads on one core. In either case, all of these machines, you might be running two threads of execution actually at the same time, and there you also have concurrency. This can cause, and I guess if we want to be really complete, we should maybe talk about DMA as well, but never mind. So when you have this shared memory, then the plus concurrency leads to race conditions. So a race condition is where you are accessing some shared memory without synchronization. So there's no guarantee that that bit of memory isn't being accessed at the same time by some other thread. And if it is, you could get weird effects. Race conditions usually just don't show themselves, except when you're trying to demonstrate it to a customer. Okay, so to protect ourselves against race conditions, we need synchronization. In particular, mutual exclusion or locking. So there we acquire a lock using an atomic instruction that guarantees that only one of us gets the impression that we own the lock. The atomic instruction would be something like test and set, or compare and exchange, or lock swap I've seen. Basically they all do the same thing. They see, is this value 0, let's say. If so, set it to 1. And you can't have two threads at the same time running that atomic instruction and both having the same experience of, yes, it is 0. The hardware guarantees that only one of them will see it as 0, and therefore only one of them will successfully set it to 1, and the other one will see, no, it was 1 already. Okay, so using this kind of locking, we can guarantee that during a critical section, which is delimited by an acquisition and the release of a lock, only our thread gets to run. So this eliminates race conditions, but instead leads to deadlocks. And deadlock generally also do not always appear, but they prefer to appear when you're demonstrating. And here, the whole thing just stops running. It's caused by a circular dependency, but not just that. Right? There's 4 different conditions that all have to be true in order to get deadlock. You need to have, let's see, what's it called? Something and hold. Hold and wait. That's good. Hold and wait. Hold and wait. Any other bids? Mutual exclusion. Right? Without locking, we won't have anything. And there's one more.
Poly exclusion?
Sorry?
Was it poly exclusion?
Poly exclusion. I've never heard of that.
I don't know.
The thing is, you don't get to take the stick from another philosopher, right? There's no preemption. So you grab the one stick, and then you wait until you get the other one, with no limit. While you're holding the stick, no one else can use it at the same time. No one can take it from you, and you're waiting for the next guy, who is in turn waiting for your other stick. So now we're in deadlock. I guess you can't have circular dependency if there's only one lock. It's a nice way to avoid deadlock. Just have one lock. Makes things easy, but tends to make things slow, because that really serializes all your critical sections, and that can be an issue. If we were to eliminate one of these, then you can't have deadlock. The preferred way is to eliminate circular dependency by enforcing an order of lock acquisition globally across all locks in your system. Another way you could imagine is to not hold and wait, for example. So you try to acquire a lock, and you see, let's see, you acquire one lock, and you try to acquire the other one, and you see, no, I couldn't do it. So then you release the first one. But if you do that, then you could end up instead with a live lock. There's lots of work being done, but no progress. So in deadlock, everyone's waiting. So live lock in the philosopher case would be, I put down the one stick, try to take the other one, I can't. So I take up the first stick, I try to take the other one, I can't, so I put down my first stick. And then I try to do the same thing again and again and again. And I never get the 2 sticks at the same time. Okay, so interrupts are an important part. Both interrupts and signals are an important part in this discussion here when you're in operating systems. We have a whole lot of concurrency from interrupts. They keep going off. And the OS has all these shared data structures that we need to update in response to interrupts, but we shouldn't really be acquiring locks. Right? Because if we try to acquire a lock while you're in an interrupt, if someone else is holding a lock, holding that lock, then you will not return from the interrupt, and it's over. So what they do in XV6 is just disable interrupts. Whenever you're holding a lock, you disable interrupts. So now you'll never end up in a situation where when you're in an interrupt, someone else is holding the lock that the interrupt wants. You can't get that kind of deadlock. Why do we get a deadlock here? It's a circular dependency, sort of an implicit circular dependency. It's between one lock only and the CPU itself. So you can have this deadlock with just one lock in this case. So now we grab the lock, an interrupt goes off that tries to grab the lock, but it can't because it's taken. And now the interrupt handler will just spin forever trying to get the lock, and so will never return so that the original code can release the lock. So you get a circular dependency kind of by surprise, even though you had only one lock. You don't generally see that in application code, except in signals. If you try to acquire a lock in a signal handler, and that lock is being held by your normal code, you have the same situation. So just don't do it. Okay. We have a few more minutes. Scheduling, yeah. The XV6 scheduler is very simple. It's called round robin. Plenty of other ways that you can do scheduling. Would be a good idea to refresh a little bit on alternatives that are in the textbook, and perhaps at least taking a look at the Linux completely fair scheduler, the CFS, which is sort of accepted fine scheduler. It has all sorts of, it's a huge bag of features, this completely fair scheduler. We talk about a very simple model here. But it has all these different options that makes it an enormous beast that you can't actually have in class. But there you are. Okay, so finally we should talk about permanent storage. Generally, we deal with block devices, 512-byte blocks. You can read a block or write a block by number. Whoop. And that's about all that a block device provides. If usually we want something a little more sophisticated than that, somehow the accepted sort of convention among computers overall has become this thing with directories and files. I don't think it has to be like that. It's not obvious to me, but that's just how it is. So file systems provide this interface. A directory is a list of names and associated inode numbers. It may not be called inodes in NTFS, but it's going to be pretty much the same thing. It's the name is naturally the same thing, and this is going to be some sort of identifier for the actual file contents, which is a group, ends up being a group of those blocks. You use the inode number to look up a metadata structure that says something more about the group of blocks, how many there are, and who owns them, and which ones they are. Right? That's the purpose of the inode. Okay, so the name of the file generally exists only in the directory. It's not part of the inode, although there are file systems that kind of merge the two concepts together. And let's see, and then there's your inode, which is some metadata, size, owner, permissions, and then a list of blocks. So how we represent this inode can vary dramatically depending on the file system. We've talked mostly about the Unix style kind of strange tree with some direct blocks, one indirect block that points at multiple direct blocks, and the double indirect, treble indirect. But you can do it in the fat style, where there's one big table with a bunch of with numbers saying which is the next block, which is the next block, and so on. Or you could do it in the balanced tree or the B tree style, like in BetterFS or in the Mac HFS or in ZFS or in NTFS, where they have a tree that represents the both the inodes and sometimes the data as well, and perhaps even the directory names. Different on-disk representations, but the sort of general interface is directory is an inode that contains, really is an inode that contains a list of names, and an inode is this sort of thing, and a file is just an inode. Right? Plus a name in one or more directories. I should go the other way. One or more names. Okay, so you'll want to review how the sort of the Unix inode is structured, and also how the x86 file system manages free blocks, how a delete of a file works, how you create a file, how do you find an inode, how do you find a free block, right? That sort of thing. Like, just how is this thing built? It's not because this thing is built in a particularly great way, but if you see how one simple one works, at least you have an idea of how a simple one works. That's, then you can make more complicated ones if you want. Let's see. Right. We worried quite a bit about persistence. So a few nice pieces here. One was logging file systems. Let's see, atomicity or transactional semantics. Atomicity through logging. So with a logging file system, you first write to the log, and you might want to review how x86 does this too. It's really simple. The log has one entry in it. It says, like, this is the block I plan to write to here, and that's it. And then, or maybe it was these blocks. Yeah, there's going to be more than one block, but basically there's one transaction. Yeah, there's one transaction that these are the blocks I want to write to these places, and then it goes and does it. So write what you plan to do, and do what you plan to do, then write that you did it. Right? So, or maybe log that you did it. The beauty of this is that no matter when power fails, you're guaranteed to end up with a consistent system if upon boot you go through your log and do everything that you planned to do, but you never did. Right? And you end up with the intended system, intended file system. And we also talked about RAID to manage, to handle disk failures. So if an entire disk dies on you, how do we handle that? Basically, with RAID, we just make a bunch of copies. There's RAID 5 that has these that saves some disk by doing a parity disk instead of just a straight up copy. And there's RAID 0 that stripes across multiple disks, increasing the risk of failure, but also increasing the performance, sometimes significantly. And of course, you also get a much larger volume, right? If you tack together 20 disks, you get one apparent disk that's 20 times the size, and that can also be convenient. And then, of course, there's backups. All of this stuff can be stolen, or burned down, or blow up. So it's best to keep a backup somewhere else. Okay, and then finally there was permissions management. So the OS is in charge of making sure that one user doesn't do something that another user wouldn't want it to do. In a multi-user OS at least, and Unisys at least are all multi-user. So we see this in the file systems. We have owners of every file, and specific permissions for the owner versus other people versus groups and so on. And the operating system also maintains other checks. Right? If you try to kill a process, it would. Well, x86 doesn't. x86 doesn't support multiple users. Maybe a future homework. but a normal Unix would keep track of who you are, your process, a certain process is running on behalf of a user, and then if that process tries to kill another process, it's only okay if it belongs to the same user, or if the assassin here happens to be super user, in which case it's also fine. So it's the purpose, it's sort of the duty of the operating system to check a bunch of different conditions to make sure everything's fine before going ahead and doing the dangerous thing on behalf of the user. And that's pretty much what the OS does all the time. The OS provides some safety, and then it provides some convenience features. We talked about alternative OS designs toward the end here, where the OS doesn't provide any convenience features. That's all into up to a library and user space, and the OS only provides a minimal set of safety features, and that would kind of fall in the exokernel category. Okay, that's it for the semester. It's been a pleasure having you. I'll be happy to answer any further questions on Piazza or here after class. Don't forget to fill out your teaching evaluations if you haven't already. I also would encourage you to put teaching evaluations on Rate My Professor. UIC doesn't make the evaluations public, and so I think it's nice for students to kind of see what to expect. So Rate My Professor, there's a big profile. I try to compete with the lower level professors that teach hundreds and hundreds of students in the number of reviews, not the quality of reviews perhaps, but at least the number of reviews. So do post a review if you want to. Other than that, thanks a lot and good luck with the exam. And maybe I'll see you in the fall. I won't teach in the spring, so I'll be around. All right, thank you.